Hey fellas, I've been in this study room for like the last 3 hours. This is my script. I was going to do a skit where I played two characters, and this script ended up taking a really long time, and also it apparently is really hard to do a skit with yourself, but you can't hear yourself doing other lines, and I have no time left, and I'm really low-key stressed, so we're just going to do the example problem in the skit, not in a skit, so I don't pull all my hairs out, and also I'm pretty sure if I committed to that, I would not have time, and the library would close, and I'd be very sad, because it is Tuesday evening at, like, 10:30. So, what we're going to do is some trig sub, which is a it's an integration strategy that we didn't learn too much about, because no one really cares. But I do, because I'm a geek. So, let's do that. First of all, we're going to need to know some trig stuff. So let's do a bit of a refresher on some of our trig. A squared plus b squared equals c squared. We know this to be true. Now, let's solve for a and let's solve for c. If we're solving for c, we already have the c isolated. We just need to take the square root of it so we get the regular c, which means we'll have a square root sign over the rest of this stuff, which doesn't get any nicer. So that just turns out to be a squared plus b squared underneath the square root. A is similar, but a little bit more complicated because you don't have the a term isolated yet. So you're going to multiply that over here, which, sorry, not the a term. You're going to subtract the b term over here, leaving the a term alone, which would be c squared minus b squared is equal to that a squared. And then, of course, you'll take the square root of that, which ends up looking like c squared minus b squared in that square root. It doesn't get any nicer. That's what you're going to look for. You just need to know how to substitute out the side length value for this crazy term. Of course, forgetting to label the side lengths. That's what we're working with. So, we know that a is equal to the square root of c, this is really hard to do because it's mirrored for me, c squared minus b squared in that square root. So if we wanted to, for instance, substitute that out, we could, right, like that. Pretty cool, right? Pretty freaking dope. Where'd my eraser go? I'm so glad I'm not doing a skit anymore. That was, creative expression, I can't do it. I can't do it because I don't know. I'm scared. I'm scared of failure. And you can. I said this in class. You can get creative stuff wrong. You can't get right answers wrong, can you? Anyway, we can also take out the c and replace it with that whole thing. The square root of the a squared plus the b squared underneath the square root. You just put that in for c. Pretty nice, right? Our example is going to only work with the first kind, where you put one here, but it works essentially the same way, and all the steps of the trig sub are pretty much the same. If the crazy term is the long side, but that's not what we're working with. So our integral is going to be from root 2 to 2 of 1 over t, and yeah, I'm using t, not x. I'm sorry, not sorry. If I have to be forced to use t and not x, I will force you to learn trig sub with t's. We got this going on. So we have 1 over a lot of gross stuff. And if we take a look at that, how are we gonna integrate? How are we gonna integrate a gross thing like that? Well, you won't. Not really. It's kind of awful and terrible. So let's use some trig sub. If you take a look at this, you might notice this term right here. What is this factor here? What does this factor look like? What does it look like? It looks like one of the trig things that we just frickin' did. So if we draw in a triangle, which is how you'll always start this. These problems always start with drawing a triangle. Trust me, I tried to skip it when I was learning. It did not go well. You gotta have the triangle. The triangle is paramount to your success. So we can see that we have a squared term minus a squared term, which means, as we saw, this will be one of our shorter side lengths. So let's just put that gross thing right in there. That's our gross little side length. The one that it's being subtracted from is the squared long side length. So we can put in a t right there, which is, of course, the square root of the t squared. And then the one that's subtracting from the thing is the square root of the short side. So we'll just put a 1 there. And that is our triangle we'll be working with. You might be thinking, that doesn't help us solve this. That's the timer for my my previous attempt at the skit, because I need to limit this to 20 minutes, and the skit was quickly becoming way more than that, so I set a timer, and I never forgot to turn it off. Okay, well, this is little vlog style thing, I think is much better. Because I don't have to be creative, preemptively. I can just yap at the camera and do math. The only hard thing is like writing this, putting my face in the shot and being like, look at the math. Anyway, man, I bet that was horrible to watch in class. Sorry, Hazel. Oh, right. How's that gonna help? Doesn't look like it's helping. Oh, it will, don't worry. Anyway, of course, we've already established that this is not gonna work with any of our strategies, like IBP, USub. It ain't gonna work. Like, he could try, but it don't work out. Trust me. It might. I don't know. I'm guessing it doesn't, if this is an example of trig sub. We'll assume it doesn't work, because usually that's when, if you can use IBP or USub, just do that, but I don't think you can. Anyway, you'll note it. Where's my green pen? Where's my green pen? Green pen. Green pen. Green pen. Green pen. Ooh. Notice those three things? Those are three factors with t. If we want to use some substitution, we gotta get all the t's out. You know, when you're doing sub, you gotta get rid of all the things and replace them all with u's. Well, we're gonna do the same thing, but not with u's, or not with u's. We're gonna use this guy, theta. We're gonna use this fella. It's gonna be our knight in shining armor. Well, you will also return, but we can put that on the bench. You got benched. Anyway, this middle one right here, with the gross square root, we can see 1 over the big thing. Now, if we look over here and think of let's just think of some trig functions in terms of theta, this specific theta. You have your sine, your cosine, your tangent, secant, cosecant, and cotangent. Those are your 6 options. And with those will be equal to different things. Like, for example, sine of this theta is going to be opposite over hypotenuse, which is just the square root of t squared minus 1 over t. Or you could do cosecant, which would be the hypotenuse over the opposite, which is, I guess, just the inverse of sine, which is the one I just did. Anyway, there are a couple of ones that might help us out. Let's look at cotangent theta, for example, which is, of course, adjacent over opposite. And adjacent is 1, and opposite is the gross thing. So we have cotangent theta is 1 over gross thing. And look at that, in here, wait, 1 over gross, cotangent 1 over gross thing. Look at that, 1 over the gross thing is in here, so we can just substitute that out. Makes it much easier. We'll also notice that we have the 1 over t cubed, which we don't have anything super nice for, but something we can try is the this is really awkward. I might have to re-record the whole thing without holding the camera, which would probably be a lot better. Anyway, the cosine of theta is 1 over t, which is close. 1 over t is close to 1 over t cubed, but it's not quite it. What happens if we cube both sides, however? That results in a nice little 1 over t cubed, and would you look at that? That's what we want. Congratulations, cosine cubed is the key here. I really wish that wasn't reversed, because I could actually reference to myself what's happening on the board with the screen, but it just doesn't want to work like that. Anyway, dt. dt is the gross one. It's fine. What we can do is we can just get a trig. Our favorite one is when we can get just the variable by itself in the numerator. That's the easiest. And would you look at that? If we did this side over this side, we'd have that, which is just t over 1. T over 1 is just t. So that ends up being the hypotenuse over adjacent, which is secant. So we can do secant theta is t. If we want dt, we gotta do the whole. It basically looks like u sub. Imagine the theta is a u, but also don't. You'll see how it works out. If we were to derive both sides, t is just 1, and then the secant theta is the secant theta tangent theta. And if you remember from the u sub stuff, you put the d theta and the dt. There we go. It looks pretty similar. That's how it works out. There's some simplification. I don't want to get into it. It's boring. But look, delicious, dt. So we're gonna take our big old thing and replace all the things now. We know. Can you see this? Okay, you can. Okay, we're gonna hope you can see that. From root 2 to 2, we have 1 over t cubed, which we know is just cosine cubed of theta. We have 1 over gross thing. We know 1 over gross thing is just the cotangent theta. And then we have dt, which is, I drop my pen every fucking recording. I'm gonna lose my mind. Yeah, dt is that big ol' thing. So we just put that big ol' thing right in there. We got the secant theta, tangent theta, d theta. I'm realizing that the mental anguish of taking on a project that's too difficult for me has just been replaced by that physical pain of holding my left arm up for like 20 minutes. Anyway, let's turn these all into just cosine and sine terms, because that's much easier to work with. Cosine cubed theta stays the same. Cotangent theta is cosine over sine theta. Secant theta is 1 over cosine theta, and tangent theta is sine theta over cosine theta. If we take a look at this, we can use like exponent rules to simplify this pretty easily. Oh, there we go, there's the whole thing. We have in the numerator 4 cosine total, 3 plus 1. So we have 4 there. There's 1 sine in the numerator and denominator, which just cancel each other out pretty easily. And there's 2 cosines in the bottom, which end up being 2 in the bottom. So you have 4 on the top, 2 in the bottom, which end up being just 2 in the top. And that's the whole thing. So we can just take it all out and put in our cosine squared theta. I know it might be hard to track this. I'm sorry, but I'm going to run out of board space, and I have 5 minutes left. You're probably not even going to see this. Whatever. So, let's integrate this. This is much easier, right? Wrong. It's gross. You know what's less gross? Cosine theta regular. Turns out there's this neat little trigonometric identity that turns cosine squared theta into cosine 2 theta plus 1 over 2. So we can just do that in. There's a whole thing. Honestly, like if you have a gross trig thing you can't integrate, just look at some trig identities. Something might work out and make it easier. This one happens to algebra out to one that we like a lot more. We can just take this 1/2 out, which I will elect to do because I hate when things are needlessly cluttered. And we got, this is pretty simple. We got 1/2, and then the integral of this, it ends up being, this is like a baby u sub, is 1/2 sine 2 theta, and then plus theta, I think. Is that how I had it work out? Let's make sure I'm not lying to you all. Am I lying? Am I a big liar? Y'all, I'm a big liar. Oh my god, am I a big liar? What's going on? Okay, you know what? We're going to... It's fine. Just for me, we're going to work it out the different way, because I might be lying to myself. Anyway, we're going to set 2 theta equal to u, and 2 theta equal to u ends up also being du to d theta. Basic u sub here. I'm so gonna run out of time. That's a big-ass lower bound, holy moly. Cosine 2 theta ends up being cosine of u plus 1. And then the du, if we do some algebra here, the d theta turns into du over 2. So we can just write du here and then take that 1/2 to the outside, because that's much easier to work with. And that's pretty easy to integrate. We have 1/4 times sine of u plus u. Let's remember our bounds, original bounds. These bounds are in terms of t. You probably saw none of that for Rick. Anyway, take a good look at that. We turned that 2 theta into a u. The d theta ended up being a du, and now the whole thing is 1/2 as large. This turns into sine. Very simply, the 1 is a u. And, okay. I think that's... I'm gonna go on my knees. There we go, now we're at eye level. I'm approaching my time limit, holy. Is the rest just... Okay, this is pretty simple from here. Not pretty simple. There's... I don't know, you'll see what I mean in a second. So now we can plug in our thetas for our u's. We know u is equal to 2 theta, so we know this ends up being sine of 2 theta plus 2 theta from root 2 to 2. And now we can plug in, we can go all the way back to our t terms and plug those in for our, you know what. This is gross. Sine 2 theta is gross. We only know theta. We can't do that. But we know a trig identity, don't we? Sine of 2 theta ends up being, I believe it's 2 sine theta cosine theta. Yep. 2 sine theta cosine theta. I promise I'll show you in a second. I just need to write this out somewhat quickly. We have the sine 2 theta ends up being 2 sine theta cosine theta, and then we just had our plus 2. We've had our plus 2 theta. We know we can get a value for the sine theta and cosine theta in terms of t, that's pretty simple. And then 2 theta is a little bit worse because we don't necessarily have that in our triangle by itself. But we can use the inverse trig terms to make that work out. We're going to quickly reference up here. We figured out that cosine theta is equal to 1 over t. Oh, I just realized I'm over 20 minutes, but I can just have Nava, who's going to help me. You don't know Nava, it's fine. I'm gonna go into if I'm not Photoshop, video editor. We're gonna speed it up so it ends up being 20 minutes. This is a hard watch. I'm sorry. This is great. I'm confident in myself and my project. The project that I realized was way too much for me. Anyway, back to the math. See, the math is where the comfort's at. I don't have to worry about creative expression. This is where we'd like to start when getting rid of the gross. Is that where we want to start? Am I losing it? Yeah, that works out. Anyway, so we're trying to solve for theta here because we're trying to substitute out this theta. You may know that a cosine inverse will undo this cosine and leave us just with a theta on this side. And to be clear, I am doing a cosine inverse for the whole thing. So this ends up being cosines, and these undo each other, just give you a theta. And then we have the arc cosine, which is the same thing as the inverse cosine, of 1 over t. So we can plug that in for our theta. And that ends up being, well, we got to figure out what our sine and cosine terms are, right? We already know what the cosine is. It's 1 over t. We also need to figure out what the sine of theta is. That ends up being relevant here, which is, going back to our triangle over here, the opposite over hypotenuse, which was the t squared minus 1 over t. And we know cosine is 1 over t. So sine times cosine ends up, oh, also, something we can do here is both of these terms start with a 2. So this is like our greatest factor. We can just multiply the whole thing by 2, which ends up taking this from a 1/4 to a 1/2. That just makes it easier to look at and work with, which is great. So that ends up being equal to 1/2. And then we know sine is square root of t squared minus 1 over t times cosine theta, which we know is 1 over t. And if we multiply this by 1 over t, this stays the same and we just make this a t squared. This ended up just as this. And then plus theta, we know theta is the arc cosine of 1 over t. Now, the arc cosine is a really funny function because a lot of numbers don't work for it, but because this problem works, these bounds, when plugged into arc cosine 1 over t, do work out. I could go through all the algebra that gets you to the exact answer and whatnot, but that'd take a lot of time, and I'm already at 24 minutes and 17 seconds, so, man, my skin's not good right now. It's fine. We're going to leave this as is, because we've integrated this, and we're back to, oh, we cannot forget our bounds. We would just use the fundamental theorem of calculus to get the answer for the whole integral. But that's a lot. And this is integrated, and it's in terms of t, which is what we started with, so I'm good to stop here. If you are curious, the exact answer ended up being, sorry, I did say exact, I meant approximate. I didn't actually write the approximate answer, because I low-key hate them. But the exact answer ends up being root 3 minus 2 over 8 plus pi 24ths. And the pi came from the arc cosine because it comes out as radians, because radians have no unit, I think is the correct answer. And then that whole thing is just that. You can kind of see how it's structured kind of similarly. Anyway, that's trig sub. Essentially, you have your triangle that you set up using something that looks like this in your integral, and then you'll use this triangle to figure out all the trig terms that you like. That trig terms that end up being something terms of t or what x or whatever variable you start with. You plug all those in, which will simplify to something. Here we ended up having to use a trig identity to then integrate. That's not explicitly part of trig sub, but that was a part of this problem. But yeah, you're going to, it's calc u sub, but just with specifically using trig. You substitute your variable for theta, you integrate, and then you take your big old theta thing, take it all the way back to something in terms of t, and then you do FTC, and you get your answer. It's It's just you,